All right, this is for students that were absent this week, which is the week of September 30th. So September 30th, October 1st, 2nd, and 3rd, these are the things that we did. So we did some review yesterday, which I sent home as an email. I sent the study guide and then the corresponding Unit 2 matter packet. So that's what we started yesterday. You should be able to do all of it after you watch this video. So the first thing is you need to get out your note packet. Remember this guy? It says on the top, Chemistry Unit 2 Matter. If you're honors, it says honors. So the content for this is about the same for both regular chemistry and honors. So this video is for both of you. You need to turn to page 6 and you'll see at the top, heating curve of water. Okay, heating curve of water. So I'm going to show you what the heating curve of water is. So it looks like this. Okay, this is an X and Y axes. Please draw this carefully in your notes, and I suggest you use a ruler. The Y axis is temperature. And what are the units that we always use for temperature in chemistry? Celsius. Yes, so degrees Celsius are the units. Down here, we're going to just put heat added. And for those of you that know, the energy unit that we use is joules, but you don't need it yet, so I'm just going to write heat added. So we start with a piece of ice that's just come out of a deep freezer. Very, very cold. So I'm going to call it around -50, okay? And you can do your axes by 25s. So -50, -25, 0, 25, 50, 75, 100, 125. That's about as high as we need to go. Okay, so you start down here, and this is our coldest piece of ice. And as you add heat, what's going to happen to the temperature? Well, when you add heat to anything, the temperature usually increases, right? So it's going to increase until it gets to 0. Now, why does it stop there? Because we usually think that if we keep adding heat, the temperature is going to keep going up, but it doesn't. It actually stops there and it goes flat. So what's happening during that flat period? I'm adding heat, but the temperature isn't increasing. Well, this is when the solid that was right here is turning into liquid. Okay, liquid right there. This process, solid going to liquid, what is it called? Picture solid water or ice turning into liquid. What is that? Melting. Good. So melting. The reverse of melting, just so we can have a vocab review, the reverse of melting is freezing. Good. Okay, so reverse of melting is freezing. So as I add heat, up, 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 at 0 degrees it stops, and all of the energy is going to melting. Why is that? Well, as we're going from solid ice to liquid water, bonds are being broken. Okay, so normally solid ice looks like, I'm going to do it up a little higher, looks like this. So we've got these little water molecules. And they're actually very rigid, okay? They're extremely rigid. So these little dotted lines are like bonds. And they are held together by these little bonds called hydrogen bonds. Okay, and this structure then is repeated throughout it. So in this two-dimensional picture here, each water molecule has 1, 2, 3 bonds holding it to other water molecules. Now there's also 3-dimensional bonds, so that's even more. Now during liquid phase, what happens is these rigid structures become more fluid. And what does it look like? When it melts, it turns into liquid And now these molecules are actually much more random. Just want to keep the number the same. And they're kind of haphazardly bonded together, okay? They're no longer bonded 3 bonds per molecule. You maybe only get 1, 2, 1, 2, like that. So some of the bonds are broken. To break those bonds, it takes energy, okay? Just like it takes to break most things. So like imagine 2 people holding hands, someone coming up and breaking the hands apart. In order to do that, it takes energy. So in order to pull 2 molecules apart from each other, it also takes energy. Okay, so these attractive forces have to be overcome. So that's what's happening here. All the energy or the heat that you're adding is not going to increase the temperature, it's going to break those bonds. Now once it's all those bonds, the needed bonds are broken, now as you add heat, the temperature increases until you get to 100. What's special about 100 degrees? That's when the water boils. Okay, so here we have boiling. 100 degrees Celsius, it boils and it all turns to gas, okay? And then once it's all boiled, as you add more energy, the gas temperature increases. Okay, so this is flat for the same reason that this is flat. But if you notice, I drew this one longer. Why did I draw it longer? Well, because when it goes from liquid to gas, so it boils, the gas molecules now no longer are attracted to each other. They're just scattered randomly with no attractive forces, or virtually none. So this takes a lot more energy. So this requires more energy because all of those bonds between the molecules need to be broken. Okay, they need to be completely overcome, completely broken. So more bonds are broken, so more energy is needed, okay, or more heat is added. So that's why this one is much shorter, this one is longer, okay? So this is what's happening on our heating curve of water. Now the reverse of boiling, what's the reverse? Remember the vocabulary word? Condensing or condensation, this process going backwards. Okay, so now we're going to answer 5 questions about this curve. Okay, question number 1. You need to write these down as well. Question number 1. What is the melting point of ice? So we find the first straight part where the first phase change occurs, and that is 0 degrees. So make sure this is at 0 degrees on your graph. Okay. When is the boiling point of water? So we find the second flat region, and we look over, it's at 100 degrees. So the answer to question number 2, what is the boiling point of water? It's 100 degrees. Okay, question number 3. Why is this flat? Why is this flat instead of slanted? Okay, well, flat means there's no temperature change. Why is there no temperature change? Because the energy is not going to increase the temperature, it's going to break the bonds. Okay, so break the bonds between the molecules. Okay, question number 4. Why is boiling part longer than the melting region? The boiling part is longer, it means that more heat is added, right? Because that's why it's longer. It requires more heat. Why does it require more heat? Because when you boil, when you go from liquid to gas, we are breaking all of the bonds, okay? We're breaking all of the bonds. Whereas when we're just going from solid to liquid, we're just breaking some of the bonds. See, there's still bonds here, 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 here. There's still bonds going on, okay? But more is needed because more bonds are broken. So I'll just summarize that one more time. Why is this region longer than this region? Because more energy is needed to break all the bonds of the liquid molecules to become gas molecules, whereas less bonds are broken when you're going from solid to liquid. Okay, if you need to rewind and watch that again so that you can write it down, then go right ahead. So that's the heating curve of water. I also want you to review your dry ice lab, because your dry ice lab is going to be a question on the test, and I will be posting a video later that's going to help explain the dry ice lab to you. So you should look for that tomorrow in your email. Okay? I hope you all are being safe at home, and I hope you're still continuing the learning process there, and I hope this helps prepare you for your exam.